Welcome to Wisdom Docs. Let me tell you something strange before you drift off tonight. Beneath the deepest oceans, far below the reach of any light, there is a recording. Not a recording anyone made, not a tape anyone pressed, or a disc anyone cut. The planet made it, slowly, without intending to, the way a riverbed keeps the shape of every flood it has ever carried. The floor of the sea has been recording something for 200 million years, and the thing it has been recording is the Earth's own magnetic field, flipping over again and again, north becoming south and south becoming north, across spans of time so long they make a human life feel like the flicker of a single frame. Stay with that image for a moment. The sea floor as a tape recorder. A long, dark ribbon of stone laid down strip by strip, each strip catching the direction the planet's magnetism happened to be pointing on the day that stone was born. And then the next strip, and the next, each a little younger than the one before, marching outward in both directions like the rings of a tree that grows sideways instead of round. You could read it if you knew how. You could run your finger along it and feel the planet turning its compass over and over through the ages. For most of human history, nobody knew it was there. Nobody knew the stone could remember. And the people who finally learned to read it were not even looking for it. They were looking for something else entirely. But we will come to that. For now, let your shoulders go heavy against the pillow. Let the day you just lived begin to loosen its grip. There is nowhere you need to be inside this story, and no part of it you are required to stay awake for. If you drift off in the middle of a sentence, that is exactly right. The story will keep going gently in the dark, and so will the planet. Because here is the other thing, the closer thing, the thing happening right now, right under you, even as you lie still. The ground beneath you is moving, not in any way you can feel, not in any way that should worry you, but moving all the same. The great slabs of rock that carry the continents and the ocean floors are sliding very slowly across the hot and yielding interior of the Earth. And the speed at which they move is one of the most quietly astonishing numbers in all of science, because it is a speed you already know in your own body. The plates move at about the rate your fingernails grow, a few centimeters a year, slower than you could ever watch. So slow that within a single human lifetime, the change is barely the width of a few hands. But give it 10 million years, give it 50, give it the patience the Earth has always had, and that fingernail crawl carries whole oceans open and slams whole continents together and lifts the floor of the sea up into mountains that scrape the sky. That is the strange truth you can fall asleep on tonight. Everything that feels permanent under you, the bedrock, the bones of the land, the continents on the map you learned as a child, all of it is in motion. Just at the speed of a growing fingernail. The world is not still. It is only patient. And here is the puzzle at the heart of everything we are going to wander through tonight, the master enigma, the question that took the better part of a century to answer. It seems, when you first hear it, like the most obvious idea in the world. Look at a map of the Atlantic Ocean. Look at the eastern coast of South America, the great rounded shoulder of Brazil pushing out toward the east. Now look at the western coast of Africa, the deep curved bay of the Gulf of Guinea waiting to receive exactly that shoulder. They fit. Not perfectly, not like cut paper, but unmistakably the way two halves of a torn page fit. The bulge of one slides into the notch of the other. A child can see it. A child has seen it many times, tracing a finger along a school globe and wondering why the pieces look as though they were once pressed together. So here is the puzzle. If the fit is that plain, that easy to see, that almost anyone can notice it in an idle moment, then why on earth did the world's most serious scientists laugh the idea out of the room for 50 years? Why was the man who finally argued it properly mocked, dismissed, called an intruder and a fantasist? And what, in the end, finally proved him right, decades after he was dead and frozen in the ice when his own evidence had never been enough? That is the journey tonight. The obvious idea that was ridiculed, the good reasons, the genuinely good reasons that the ridicule had behind it, and the wholly unexpected thing that finally settled the question, written all along on the floor of the sea, waiting for us to learn its language. There is heartbreak in this story, and there is wonder, and there is a kind of justice so slow it arrived only after the man who needed it was gone. But it is a gentle story, all of it told at the pace of drifting snow. Before we go deeper, a small thing, the way we always do here at the docks, I find myself curious, lying here in the dark with you, where in the world you are listening from tonight. What land is under your bed right now? What continent, what coastline, what piece of the moving earth is carrying you slowly toward morning? If you feel like it, leave a word in the comments and tell me where you are. I read them, all of them, and there is something lovely about a quiet crowd of people scattered across the whole drifting surface of the planet, all settling down to the same slow story. And if you are new here and you would like more nights like this one, more slow journeys into the deep and the strange and the old, you are welcome to subscribe and stay a while. There is no rush, there never is here. Now let your eyes close if they want to, and let us go back more than 100 years to a cold lecture hall in Germany, and a man who was about to make a mistake that would also somehow be the truth. His name was Alfred Wegener. And the first thing you should know about him, the thing that mattered enormously to how his idea was received, is that he was not a geologist. He had no business, as far as the geologists were concerned, telling them anything at all about the rocks and the continents and the long history of the Earth's crust. Wegener was a German meteorologist, a weatherman, his critics would say, with the particular contempt that experts reserve for an outsider wandering into their field with a grand idea. He had trained, in fact, in astronomy. He had earned his doctorate at the University of Berlin in 1905, studying the heavens, the orbits, and the stars, and then he had turned away from the sky and toward the air, toward weather and clouds and the great cold reaches of the polar regions. He was a man drawn to hard places. He made his name not in a comfortable laboratory, but on the ice of Greenland, on expedition after expedition, into one of the most punishing environments any person can enter. He was an explorer in the old, demanding sense, a man who packed sledges and crossed glaciers and endured the kind of cold that kills. He understood weather because he had lived inside the worst of it. He understood the polar world because he had nearly died in it more than once. Keep that in your mind, the image of Wegener on the ice, because the ice is where this story will eventually sorrowfully return. But for now he is a younger man, a meteorologist, with a curious habit of looking at maps and seeing in them something nobody around him would take seriously. The story, as he himself told it, began with a map and a moment of idle attention. He noticed the fit, the same fit a child notices South America and Africa, the shoulder and the bay. But Wegener was not a child, and he did not let the noticing pass as a curiosity and move on. He let it lodge in him. He began to wonder, seriously, with the full weight of a trained scientific mind, what it would actually mean if the fit were not a coincidence. What if the continents had once been joined? What if they had, over unimaginable stretches of time, drifted apart, pulling open the ocean between them like a slow tide, pulling a raft from the shore? He called the idea in his own language Die Verschiebung der Kontinente, the displacement of the continents, the moving of them. And on the 6th of January in the year 1912, he stood up before the Geological Association in the German city of Frankfurt and presented this idea to a room of serious men who studied the Earth for a living, the displacement of the continents. He told them that the great land masses were not fixed, were not anchored forever where they sat, but had wandered across the face of the planet and were wandering still. You can imagine the room. You can imagine the polite, cooling silence, the exchanged glances, the sense settling over the audience that this astronomer turned weatherman had strayed badly out of his depth. But Wegener was not a man easily put off, and 3 years later in 1915, he gathered everything he had into a book. Die Entstehung der Kontinente und Ozeane, The Origin of Continents and Oceans. It is one of those titles that sounds now like the title of something that changed the world, and in the long run it was. But in its own moment it landed like a stone in deep water, sinking slowly out of sight while the surface closed over it as though nothing had happened. Now it would be easy and it would be wrong to tell you that Wegener simply pointed at the puzzle pieces and got laughed at by fools. The truth is richer and kinder to everyone involved, and it is the truth we are going to honor tonight, because Wegener did not rest his case on the coastlines alone. He was a careful man, a synthesizer, and he gathered evidence from field after field, piling it up the way you might pile stones into a cairn until the shape of the thing becomes undeniable. The fit of the coasts was only the beginning, only the loose thread that first caught his eye. He pulled on it and a great deal more came with it. Consider the mountains. Wegener noticed that if you closed the Atlantic Ocean, if you slid the continents back together along that jigsaw seam, the mountains did not merely happen to be near the join, they continued across it. The ancient mountain belt of the Appalachians running up the eastern side of North America did not simply stop at the water's edge as though the ocean had always been there. Their structure, their age, their very grain matched the mountains on the far side, the Caledonides, the old worn ranges of Scotland and Scandinavia. Line the continents up the way Wegener wanted to line them up, and the Appalachians of America ran straight into the Caledonides of Europe as though they had once been a single great range, later torn in two and dragged apart across an ocean that had not yet been born. It was as if you had found a road severed by a chasm, and on tracing it to the chasm's edge, found the very same road, the same width, the same paving, the same milestones, picking up again on the other side. The road did not stop at the chasm had opened across the road. That is a different kind of evidence than a coastline. A coastline could be a coincidence, two curves that happen to be complementary, but matching mountain ranges, the same rock, laid down in the same way at the same time, severed and separated, that is harder to wave away. The Earth had written the same sentence on two continents, and the only way to read it whole was to push the continents back together. And we should pause here, gently, to be fair to the past, because Wegener was not the very first person ever to look at a map and feel that strange pull of recognition. The noticing was old. As far back as the year 1596, a Flemish mapmaker named Abraham Ortelius, a man who spent his life drawing the known world, looked at the Atlantic and wrote that the Americas appeared to have been torn away from Europe and Africa, ripped loose by earthquakes and floods. Torn away. He used that very word. More than 3 centuries before plate tectonics, a man bent over his maps, saw the tearing and named it. Then in the year 1620, the English philosopher Francis Bacon, one of the great minds of his age, remarked upon the matching outlines of the New World and the Old, the way the coasts seemed to answer one another across the sea. He did not explain it, he simply noticed, and noted that the correspondence was too neat to ignore. And later still, in 1858, a Frenchman named Antonio Snider Pellegrini took the noticing one step further and actually drew it. He made a pair of maps showing the Americas pressed up snug against Africa and Europe, the Atlantic squeezed shut, the continents reunited into a single mass. He was looking, in his way, at the same fit, and he committed it to paper, two pictures of a world that had been whole and a world that had broken apart. So the noticing was centuries old. Ortelius saw it, Bacon saw it, Snyder Pellegrini drew it. The fit of the continents was not Wegener's discovery, and he never pretended it was. What Wegener did, the thing that earns him his place in this story and not theirs, was something harder and rarer than noticing. He synthesized. He took the loose, scattered observations, the coastlines and the mountains and, as we will come to, the fossils stranded on opposite shores, and he wove them together into a single, testable theory. He did not merely say, "Look, they fit, isn't that curious?" He said, "Here is what must have happened, here is the mechanism by which the world arrived at its present shape, and here is the whole body of evidence that all points the same way at once." He turned a scattering of curiosities into an argument. That is the difference between glancing at a puzzle and actually trying to solve it, between feeling that the pieces fit and standing up before a hostile room to declare that they once were joined. And it is worth saying, here in the quiet, that this is almost always how the great ideas arrive. Not in a single lightning flash of one lonely genius seeing what no one ever glimpsed before, but in the patient gathering up of things half seen by many, the binding of scattered noticings into one coherent shape. Ortelius felt it. Bacon felt it. Snyder Pellegrini sketched it. But Wegener built it, brick by careful brick, into something solid enough to be argued over, attacked, tested, and one day, long after he was gone, proven. The noticing belongs to many. The synthesis was his. He believed it. That is the thing to hold on to as you sink deeper into the pillow. Alfred Wegener looked at the torn coastlines and the severed mountains and, soon, the fossils, and he became certain, with the deep and steady certainty of a man who has checked his work from many angles, that the continents had moved. He could see that it was true. Everything he gathered confirmed it. The shape of the land, the grain of the mountains, the bones in the rock, all of it sang the same low note, and the note was this: it was once together, and it has come apart, and it is moving still. But there was a hole at the center of his beautiful, careful theory, a single missing thing, and it was the one thing that science in the end could not forgive him for lacking, because Wegener could tell the world that the continents had moved. He could show from a dozen directions that they must have moved. What he could not do, what he could not for the life of him explain, was how. What force could possibly be great enough to take a continent, a slab of rock the size of a hemisphere, weighing more than the mind can hold, and shove it across the surface of the planet through solid stone? What engine drove the drift? What hand pushed the pieces apart? He had guesses. He reached for the forces he knew, the ones a meteorologist and astronomer might reach for. And we will sit with those guesses and with the brilliant, rigorous man who took them apart. But that is for a little later, when we go deeper still. For now, let this be the thought you carry down towards sleep. The open door we will walk back through. Alfred Wegener could see that it was true. He had the coastlines that fit like a torn page. He had the mountains that ran from one continent straight into another, across an ocean that should have stopped them. He had, waiting in the rocks, the fossils of creatures that could never have crossed the sea between the shores where their bones were found. He had assembled almost a complete and convincing case for the most important idea in the history of the earth sciences. He just couldn't say why. He couldn't name the force. He couldn't point to the engine. And that one missing word, the word that should have come after how, would cost him everything in his own lifetime. It would turn his careful theory into a target. It would let the most serious scientists in the world dismiss him not as a liar, but as a dreamer, a man who had seen a true thing and could not, for all his effort, explain it. The mechanism, the missing mechanism, the hole at the heart of the work. And the strangest part, the part that gives this whole long story its shape, is that the answer to his question was already written down in a language no one yet knew how to read. On the dark floor of the oceans, he believed the continents had torn open. The proof of continental drift, the very engine he could not name, the symmetric stripes of frozen magnetism marching outward from a seam that runs the length of the sea, all of it was already there, already recorded, 200 million years of it laid down, strip by patient strip beneath water no human eye had ever pierced. It was waiting. It had been waiting all along. It would take the better part of a century to find it. It would take, of all things, a war, and ships dragging instruments through the deep water, hunting for things that hid beneath the surface. And it would arrive too late, far too late, for the gentle, stubborn weatherman who first stood up in Frankfurt and told a room full of geologists that the ground beneath their feet would not hold still. But we are getting ahead of ourselves, and the night is long, and there is no need to hurry. Let the continents drift on, a fingernail's breadth a year, beneath your bed and beneath the whole sleeping world. Let Wegener stand a moment longer in the cold lecture hall of 1912. Young still, certain still, holding his torn map of the world, not yet knowing what it would cost him to be right too soon. So picture it as a single, long ribbon of tape, the kind that once spooled inside a recorder, except this tape is made of stone, and it is 65,000 kilometers long, and it lies almost entirely in the dark beneath the sea. For 200 million years, the planet has been writing onto it, not words, not pictures, something stranger and more faithful than either. The Earth has a magnetic field, the invisible thing that turns a compass needle north, and that field is not as steady as the needle makes it seem. Every so often, on no schedule anyone can predict, it grows weak, falters, and flips. North becomes south. South becomes north. And each time molten rock wells up along that long seam in the seafloor and cools, the tiny iron-bearing grains inside it lock into place, pointing whichever way the field happened to be pointing at that moment, frozen there like a held breath, like a million miniature compasses set in stone the instant they hardened. Strip by strip, eruption by eruption, the floor of the ocean kept the record. A barcode of the planet's own changing mind, mirror-matched on either side of the seam, written down faithfully across an expanse of time the human mind can barely hold. The seafloor is a tape recorder, and it has been recording the Earth's flipping magnetic field for 200 million years. Hold that image for a moment, because we will come back to it again and again across this long night, and it is the prize at the end of the whole story. But pull back now, slowly, from the cold black floor of the Atlantic, up through the water, up into the open air, up to wherever you are lying right now. Because the same motion that wrote that tape is happening beneath you, this very second, while you breathe and settle and let the day go. The ground is moving, not in any way you could feel, not in any way that should worry you, but moving all the same, drifting, sliding, carrying the whole continent you rest upon along with it, about as fast as your fingernails grow. That slow, a few centimeters a year, no more. If you sat perfectly still for a year, the land beneath you would have carried you the width of a few of your own fingers across the face of the world. It is the slowest journey there is, and you are on it, and you have been on it your whole life without once noticing. That is the gentlest way I know to enter this story. Whoever you are, wherever you are listening from tonight, you are already a passenger on the very thing one man spent his life trying to convince the world was real. And if you would like, before we go deeper, tell me where in the world you are drifting off to as you listen. I always like to know how far this slow tide reaches. And if you are new here, and you find this kind of quiet does its work on you, you can subscribe, and the next slow story will find you when you need it. Now, the man. His name was Alfred Wegener, and the first thing to understand about him, the thing that would be used against him for the rest of his life and beyond it, is that he was not a geologist. He was a German meteorologist, a man of clouds and weather and air, and a polar explorer who had crossed the great white silence of Greenland on foot and lived inside that cold the way few men ever have. His doctorate, taken at the University of Berlin in 1905, was in astronomy. A man of the sky and the stars and the wind then, walking uninvited into the house of the rock men to tell them they had the ground itself wrong. You can imagine how that landed. On the 6th of January 1912, he stood before the Geological Association in Frankfurt and gave a lecture with a long and patient German title. Die Verschiebung der Kontinente, the displacement of the continents. A few years later, in 1915, in the middle of a war tearing his own country apart, he set the whole of it down in a book, Die Entstehung der Kontinente und Ozeane, the origin of continents and oceans, and the idea inside both the lecture and the book was so simple, so almost childishly obvious, that it is hard now to understand how it could have caused such a quiet storm. The continents, Wegener said, had once been joined. They had been a single great land mass, and over unimaginable spans of time they had broken apart and drifted, slowly, slowly, to the places we now find them. They were not fixed. They had never been fixed. The map of the world was not a finished thing, but a single frame of a film still running. And the evidence he laid out for it, the evidence he had gathered piece by piece in that careful weatherman's way, was the kind of thing that once you have seen it, you cannot unsee. Look at a map of the Atlantic, he said, really look. Look at the eastern coast of South America, the great rounded shoulder of Brazil, and then look at the western coast of Africa, the deep curving notch of the Gulf of Guinea. The bulge of the one fits into the hollow of the other. Not roughly, not approximately. It fits the way two torn halves of a single page fit, the way a key fits the lock cut for it. Two coastlines, a whole ocean apart, that look for all the world as though they were once pressed together and only lately pulled away. But coastlines can fool you, and Wegener knew it, so he went deeper than the edges of the land. He looked at the mountains. There are old, worn mountain ranges, he showed, that line up across the ocean as though they had once been a single chain that some great force had cut clean through. The Appalachians running up the eastern side of North America, and the Caledonides, the ancient roots of mountains in Scotland and in Scandinavia, share the same age, the same structure, the same character, as if you took one mountain belt, split it down its length, and slid the two pieces to opposite shores of the Atlantic. The seam of the rock, like the seam of the coast, told the same story. Things that are now far apart were once one. He was not, it must be said, the first to feel the strangeness of that fit. Long before him, others had glanced at the world and sensed something torn. As far back as 1596, a Flemish mapmaker named Abraham Ortelius had remarked that the Americas looked as though they had been wrenched away from Europe and Africa by earthquakes and floods. In 1620, the philosopher Francis Bacon noted the matching of the coastlines, and in 1858 a man named Antonio Snider Pellegrini went so far as to draw the Americas snugged up tight against Africa, fitted together like the pieces they seemed to be. But all of these were noticings, glances, a raised eyebrow at the shape of a map, and then a turning away to other things. None of them gathered the coastlines and the mountains and the rest of it into a single, testable, dangerous idea and laid it on the table and said, "This is true, and here is the case for it." That was Wegener's doing, and his alone. He was not the first to notice, he was the first to insist. And here is the thing, the soft cruelty at the center of all of it, the open wound this whole long night is going to circle. He could see that it was true. He could see it in the fit of the coasts and the matching of the mountains, see it as plainly as you can see two halves of anything that was once whole. But seeing that a thing is true and being able to say why it is true are not the same and never have been. And in science, the gap between them can be a grave. The continents had moved, of that he was certain, but what could possibly move a continent? What force, what engine, what hand could take something so unimaginably vast and heavy and slide it across the face of the planet like a ship across a harbor? He did not know. He guessed, and his guesses were too small, far too small, and the men who would weigh them knew it. He could see the truth perfectly. He just could not say why, and that one missing word, that single absent why, was the one thing the careful, rigorous, unforgiving men of the rock would never be able to forgive him for. And so let us begin there, in the evidence itself, in the things that Wegener had gathered and arranged and offered to the world, as though laying out a body of proof so plain and so varied and so convergent that a fair-minded person could not look away from it. Begin with the animals. There is a small creature called Mesosaurus. It lived roughly 280 million years ago, and it lived in fresh water, in the rivers and shallow lakes of what is now South America and what is now Southern Africa. It was not large, perhaps a meter in length, perhaps less, built low and elongate with a narrow jaw lined with fine teeth for catching fish, a creature of the shallows and the slow-moving water. And here is the thing that Wegener held up to the light and turned slowly for anyone willing to look. Mesosaurus is found only in two places on this entire planet, on the eastern coast of South America and on the western coast of Southern Africa. Those are the only places. Nowhere else in the world, in the millions of square kilometers of rock that geologists have combed and sampled and catalogued, does Mesosaurus appear. Only there, on those two facing shores, a freshwater animal stranded on both sides of an ocean 3,000 kilometers wide. The competing explanation, the one the geological establishment of 1912 preferred, was a land bridge. The idea that once, long ago, a bridge of land had connected these continents and then subsided beneath the sea, and that Mesosaurus had walked or swum across it before the connection vanished. This was not an unreasonable idea. It was the kind of idea that allowed you to keep the continents fixed in place, to keep the ocean floor firm and permanent, to keep the world you thought you understood intact. A bridge, and then the bridge sank, and the problem is solved, and we may move on. But Wegener looked at this explanation and found it wanting, not because it was impossible on its face, but because of what it required when you set it beside all the other evidence together. A land bridge might explain Mesosaurus on both shores. It would not explain, or at least not easily and gracefully explain, everything else that was accumulating. And the something else that sits beside Mesosaurus in this story, like a quiet companion, was a plant, Glossopteris. The name comes from the Greek for tongue, because its leaves were long and broad and tapered at both ends, tongue-shaped, The leaves of a fern-like tree that grew in great forests during the Permian period, somewhere between 300 and 250 million years ago. And the seeds of Glossopteris were heavy, not light, not the kind of seed the wind could carry across open water, not the kind that might drift on an ocean current for weeks and survive to germinate. Heavy seeds too dense for any known mechanism of long-distance dispersal across a salt ocean. And yet Glossopteris is found, its leaves pressed into stone, its fossil record inarguable, on every single one of the southern continents: South America, Africa, India, Antarctica, Australia, all of them. Every landmass that we now call the Southern Hemisphere once had these forests growing on it, had the same tongue-leaved tree laid down into the same rock layers at the same time in geological history, in strata that match in age and character from continent to continent, as though they were deposited in a single, continuous landscape, because, Wegener argued, they were. You cannot sail Glossopteris on the wind across half the planet. You cannot build a land bridge that connects not 2, but 5 separate land masses scattered across the Southern Ocean. The land bridge theory, which was already straining under the weight of Mesosaurus, becomes something close to impossible when you ask it to account for Glossopteris on 5 separate continents simultaneously, each one now separated from the others by deep ocean water that would have had to swallow an impossible geometry of connecting corridors. The bridges required would not be 2 or 3 temporary isthmuses. They would have to be an entire southern world of joined land, all of it somehow subsequently lost beneath the sea. And at some point, a theory that requires the ocean floor to have swallowed a second, unknown continent begins to ask more of your credulity than the alternative. There were others beside Glossopteris and Mesosaurus. Lystrosaurus, a stocky, pig-sized land reptile with a broad flat head, a creature of the Triassic world roughly 250 million years ago, found in Africa and India and Antarctica, a land animal, not a swimmer, not a flyer, not something that could have crossed deep ocean on a piece of floating vegetation and survived. And Synognathus, a wolf-like predator, of approximately the same age and the same restricted distribution, its remains turning up in South America and Africa as though placed there by the same hand, pressed into the same rock layers, occupying the same ancient world that the geology insisted no longer existed as a connected whole. Wegener looked at all of these together, and the reptiles and the plants and the mountains and the coasts, and he called the land they had once inhabited by a name. He had a gift for the right word. He called it Pangaea, from the Greek, pan meaning all, and Gaia meaning earth. All earth. The whole world gathered into a single body, a single vast landmass surrounded by a single vast ocean that he called Panthalassa, from the Greek thalassa, meaning sea. All earth surrounded by all sea. The name first appeared in the 1920 edition of his book, and it was debated and refined at a symposium in 1927, geologists and geophysicists arguing over the details of reconstruction, over which pieces went where and when the breaking began. But the name survived. It survives still. Pangaea, the word that carries inside it the whole history of everything that has ever walked or grown or rooted on the surface of this planet before the world was cut into the pieces we were born into. Try for a moment to picture it. Not a map with oceans and the familiar continents arranged in their habitual places, but something else entirely. A single mass of land roughly C-shaped if you were to look at it from above, spanning from pole to pole. The northern half of it, the part geologists sometimes call Laurasia, carrying what would become North America, Europe, and Asia. The southern half, Gondwana, carrying South America, Africa, India, Antarctica, and Australia. All of it joined, all of it touching, all of it continuous, and around it the enormous world-encircling ocean of Panthalassa, calm and ancient and uninterrupted all the way around the globe. This is the world in which Mesosaurus paddled in its freshwater lakes. This is the world in which Glossopteris spread its tongue-shaped leaves into a sky that would have looked, if you stood under it, not entirely unlike this one. This is the world before the world we know.
And then something moved, something pulled, and the single body began over millions, and then tens of millions, and then hundreds of millions of years to come apart.
Slowly, catastrophically slowly, in the way that only geological time permits, the great landmass fractured and the pieces separated, and the ocean poured into the gaps, and the Atlantic was born, and the Indian Ocean opened, and the creatures and plants that had shared a single continuous landscape found themselves, over the deep centuries, on opposite shores of water too wide to cross, marooned with their fossils in the rock, waiting for a German meteorologist to come along and read them. This was the case Wegener had built, and it was a genuinely impressive case. Taken individually, any single piece of it could be argued away, smoothed over, explained by some other mechanism. But the convergence of it, the fact that the coastlines and the mountain belts and the freshwater reptiles and the heavy seeded ferns and the land predators all pointed to the same answer, the same lost world, the same prior configuration. That convergence was not nothing. It was and remains a powerful kind of argument. In science, as in everything else, when 5 different lines of independent evidence all point to the same conclusion, you are at least obliged to take the conclusion seriously. They took it seriously enough to argue with it, which is its own form of respect. But arguing is not accepting, and accepting was not something the geological establishment of the early 20th century was prepared to do. And their reason, their central, irreducible, technically rigorous reason, was not stubbornness and was not ignorance and was not the mere conservatism of men unwilling to have their life's work overturned. Their reason was simpler and sharper and more honest than that. Their reason was this: Wegener could not say what moved the continents, and without that the theory was a picture without a frame, an answer without a method, a conclusion without a cause. He tried, he genuinely tried, and the trying is almost painful to read about now because you can feel the strain in it, the reaching for something that was not yet within reach. He proposed 2 mechanisms. The first he called Polflucht, a German word meaning flight from the poles, a centrifugal effect in which the rotation of the Earth would fling the continents toward the equator, causing them to plow through the ocean floor as they went. The second was the gravitational pull of the sun and the moon, the same tidal forces that pull the oceans toward and away from the shore twice a day, operating not on the water, but on the continents themselves, dragging them slowly westward as the Earth turns. These were not unreasonable intuitions for a man working in the first decades of the 20th century with the tools available to him. But when the physicists ran the numbers, the intuitions collapsed. The forces Wegener was proposing were not merely too small by a little, they were too small by orders of magnitude. An order of magnitude means a factor of 10. Too small by orders of magnitude, plural, means not merely one factor of 10, but many of them. 10 multiplied by 10 and then by 10 again, the calculated force somewhere so far below what would be needed to move a continent through the ocean floor that it was not even a plausible starting point for further refinement. It was not that Wegener had found the right engine and misdescribed its size. It was that the engines he had found were not engines at all, not for this purpose, not remotely, not by any reasonable extrapolation. And the man who made this case most clearly and most rigorously, the man who did the mathematics with the most precision and laid out the physical objection in its most unanswerable form, was a British geophysicist named Sir Harold Jeffreys. It is worth pausing here for a moment on Jeffreys himself, because he is one of the most interesting figures in this whole long story, and because the way he has sometimes been remembered, as the villain, the rigid conservative who refused to see the truth, is not quite fair and not quite honest, and tells us something important about how we prefer to tell stories. Jeffries was not a fool. He was very far from a fool. He was one of the finest mathematical physicists of his generation, a man who made fundamental contributions to seismology and geodesy and the study of the Earth's interior, a man whose quantitative methods transformed the science of the solid Earth. He was the kind of scientist who took the question of mechanism seriously, who understood that a theory, however suggestive its evidence, was not a complete theory until it could describe the how as well as the what. And in his 1924 book, simply called The Earth, he sat down with Wegener's proposed forces, the Polflucht, the tidal pull, and he did the calculation. He was thorough, he was careful, and the calculation showed that these forces were, to use his own language and the language the physics demanded, wholly inadequate. The centrifugal effects of Earth's rotation would not move a continent. The tidal gravitational pull of the Sun and Moon, distributed across the solid rock of a landmass, was immeasurably smaller than what would be required. The Earth, moreover, as Jeffries and the seismological evidence understood it, was rigid. The behavior of earthquake waves as they traveled through the planet indicated a body solid all the way through, a planet that did not permit the kind of flow or deformation that continental drift would require. Continents could not plow through solid ocean floor. The ocean floor was not soft, the planet was not plastic. The physics, as best as anyone could then measure it, said no. This was not dogma, this was not a refusal to look at the evidence. This was a physicist applying the laws of physics to a claim and finding that the claim, as stated, with the mechanisms as proposed, did not hold. Jeffries was right. Given what Wegener said, given the forces Wegener invoked, the theory did not work. The rejection of continental drift on mechanical grounds was, in the 1920s, a scientifically defensible position. It was the correct response to an incomplete theory. That is the uncomfortable truth at the center of this story, the thing that the simpler telling, the lone genius versus the stubborn establishment, tends to smooth over. Jeffries was not wrong to object. He was wrong to conclude that the evidence of the fossils and the coastlines could be set aside, wrong to allow the failure of the proposed mechanism to count as a refutation of the underlying idea. But his objection to Wegener's physics was, on its own terms, sound, and Jeffries, for his part, never changed his mind. Not in the 1940s when the evidence began to accumulate in a new direction, not in the 1960s when the seafloor magnetic stripes were mapped and read, and the community shifted rapidly and almost entirely to plate tectonics. Not ever. He went on revising and republishing The Earth through 6 editions, through decades of accumulating counter-evidence, through an entire scientific revolution that overturned the framework he had defended. He died in 1989 at the age of 97, still unconvinced. That is a remarkable fact. It is a strange and slightly melancholy one. He had been right about something important, the forces were wrong, the mechanism was absent, and that rightness had hardened into something that would not yield even when the world changed around it. A brilliant, rigorous, honorable man locked by the logic of his own impeccable early argument into a position that time would leave entirely behind. The wider reception was no kinder than Jeffries's, though perhaps less measured. In 1926, the American Association of Petroleum Geologists convened a symposium in New York, specifically to examine the theory of continental drift, and the examination was not gentle. Wegener was not present. His ideas were, and they were subjected to what can only be described as a formal and public dismissal. The geologist Rollin T. Chamberlain captured the mood of the room when he said, and the exact words may have been sharpened slightly in the retelling, as such things tend to be, but the substance is reliably documented. that if Wegener's theory were to be accepted, we must forget everything which has been learned in the last 70 years and start all over again. This was not meant as an observation, it was meant as an objection. 70 years of painstaking fieldwork, of stratigraphic analysis, of paleontological classification, of the slow and difficult accumulation of geological knowledge, all of it, Chamberlain was arguing, would have to be undone. The price of accepting Wegener was too high, the disruption was too great. There is something almost sympathetic in this, if you let yourself settle into the feeling of it rather than judging it from the comfortable distance of knowing the answer. Imagine spending decades learning the grammar of a language, making it yours, using it to think and see and interpret the world, and then being told that the grammar is wrong, not locally wrong, not wrong in a small correctable way, but wrong at its foundation, wrong in its basic assumptions, wrong in the way that requires not revision, but replacement. The instinct to resist is not irrational. It is the instinct to protect a way of understanding that has cost years and effort, and that still, in many of its practical applications, works well enough. The resistance was human. It was also, as we now understand it, insufficient, but it was human. And Wegener continued. Through the 1920s, he continued revising and expanding his book, refining his arguments, responding to criticism, trying to find stronger evidence for the mechanism he could not fully provide. He continued his other work, the meteorological research, the Greenland expeditions that had made his reputation as a polar scientist and explorer. He was not destroyed by the dismissal, or at least not visibly. He kept working, he kept thinking. He continued to believe, as deeply and as quietly as a person believes a thing they have seen with their own eyes, that the continents had moved and were moving still. In 1930, he was 50 years old, or very nearly 50. His birthday fell in November, and the expedition that killed him stretched through that autumn and into that month. It was his fourth journey to the Greenland ice sheet, and the most ambitious. The plan was to establish a network of winter stations across the ice, including one at the center of the ice cap, at a place called Eismitte, which means in German simply mid-ice, a point of almost incomprehensible isolation in the white interior of the world's largest island. Supplies had fallen behind schedule. The winter was coming, and the team at Eismitte was not adequately provisioned. In November, when the temperatures on the ice cap were already dropping to 50 degrees below zero, Wegener set out on a journey of roughly 400 kilometers to deliver supplies to the stranded team. He reached Eismitte. He helped deliver what he had carried across that frozen distance. And then he set out on the return journey. He did not complete it. His body was found the following spring, halfway between Eismitte and the western coast, wrapped in his sleeping bag, his face calm, composed, as though he had simply lain down and let sleep come. The cause of death was almost certainly heart failure, the accumulated strain of the journey breaking something that could not be mended at that temperature and that distance from any help. He was buried there on the ice by his expedition companions with care and with the quiet formality that the circumstances permitted. A marker was placed, and then the ice moved, as ice moves, slowly and without ceremony, and the marker and the man beneath it were carried into the glacier and eventually into the sea. His body was never recovered. Alfred Wegener, who had spent his life thinking about the movement of the earth, was himself moved by it, absorbed into it, carried away on the slow drift of things that look still but are not. He had never been vindicated. Not a single colleague of standing had crossed the floor to his position before he died. The theory of continental drift stood in 1930 exactly where it had stood in 1912, a striking and suggestive hypothesis, embarrassed by its missing engine, rejected by the physicists, doubted by the geologists, alive in the imaginations of a few sympathetic minds, but without the mechanism that would have made it science rather than speculation. The fossils were there, the coastlines were there, the mountains were there. And it made no difference because the why was absent, and science cannot live on what without why, not for long, not without someone eventually standing up and asking the one question that will not be put off. He died not knowing. He died in the ice he had gone to study, in the cold he had spent his career navigating, in the dark of a northern November, surrounded by the evidence of a planet in slow motion, unaware that the proof he needed was already written on the floor of the ocean. Unaware that it would take another 20 years and a world war and a set of instruments designed for a completely different purpose before anyone would know how to read it. The man who saw the continents move was buried by the moving of the ice, and the ice kept his secret, and the world moved on without him. But the idea did not die with him. Ideas rarely die with the people who carry them, and this one had enough of the world in it, enough of the visible, tangible, fossil-bearing world, that it could not be entirely set aside, no matter how firmly the consensus held against it. It persisted in the literature, muttered about rather than championed, referenced in footnotes, and dismissed in the bodies of papers, a hypothesis that would not quite disappear despite every reasonable cause to let it go. And somewhere in the years after his death, in the long, quiet decade of the 1930s and into the 1940s, the first suggestion of the missing engine began to take shape in the mind of another man entirely, a British geologist working from a very different direction and with a very different set of concerns. Arthur Holmes had been thinking about the interior of the Earth for a long time, and he had brought to that interior the same careful quantitative attention that Jeffreys had brought to the physics of the surface. Holmes had made his name in a field that was, in the early decades of the 20th century, transforming geology's sense of its own subject, radiometric dating. The discovery that radioactive elements decay at known and constant rates, converting one element into another in a process as regular and reliable as a clock, gave geologists for the first time a way to assign absolute ages to rocks. Holmes worked with uranium-lead decay, measuring the ratios of parent element to daughter element in ancient minerals, and what these ratios told him was staggering. The Earth was not thousands of years old, as some had believed, and not merely hundreds of millions, as the early estimates from cooling rates had suggested. It was billions of years old. Holmes's work pointed toward an age somewhere around 4.5 billion years, a figure that has proven remarkably close to what we now accept, 4.5 billion years. A number so large it resists direct comprehension, but that does something essential for the theory of drifting continents. It gives the motion room to breathe. If the continents moved at the rate of a growing fingernail a few centimeters per year, then across 4.5 billion years they could travel an almost unlimited distance. They could cross oceans. They could assemble and disperse and reassemble. They could do everything Wegener's evidence required them to do and more. Deep time is the soil in which slow processes become possible. Holmes, by extending the history of the Earth into the billions, had done something that may not have looked, at the time, like a contribution to continental drift, but was in fact foundational to it. And then Holmes went further. He looked at the interior of the Earth, at what the radioactive decay of uranium and thorium and potassium was doing, down there in the dark and the heat. And he proposed something that was, at the time, almost entirely without direct evidence, but that turned out to be, in its broad strokes, essentially correct. He proposed that the heat generated by radioactive decay in the Earth's interior was driving convection currents in the mantle, the thick layer of rock beneath the crust that makes up the great bulk of the planet. Convection is a process you can watch in a pot of water coming to the boil. The water at the bottom, closest to the heat, warms and expands and becomes slightly less dense, and so it rises. The water at the top, farther from the heat, cools and contracts and becomes denser, and so it sinks. And the result is a slow circular current. Warm material rising, cool material sinking, a wheel of motion driven entirely by temperature difference. Holmes argued in papers in the late 1920s and 1930s, and then in his textbook Principles of Physical Geology published in 1944, that the mantle, though solid in the sense that earthquake waves pass through it as a solid, behaved over the vast stretches of geological time as something closer to an extraordinarily thick, slow fluid, not flowing like water, but flowing like the thickest, most resistant substance you could imagine, a flow so slow it would be invisible to any human lifetime but real and measurable across millions of years. And if the mantle was convecting, if it was turning over in these slow thermal currents, then continents sitting on top of the mantle could be carried, not ploughing through solid rock, as Wegener's critics had correctly pointed out was impossible, but riding on top of something that was itself moving, passengers on a slow current, held up by what they floated on and dragged by it across geological time. This was the engine, or the sketch of an engine. The mechanism that Wegener had not been able to name, that Jeffreys had correctly identified as missing, that the 1926 symposium had demanded and not received. Holmes had found it, or found the shape of it, in the physics of radioactive heat and the thermal behavior of the Earth's interior. And it was a genuinely good idea, a physically plausible idea, an idea that did not require forces that were orders of magnitude too small. It was not proven, there was no direct evidence, in the 1930s, for mantle convection on the scale Holmes was describing. But the idea was there, and it was coherent, and it was waiting in the pages of a textbook that every geology student in Britain would eventually read for the evidence that would confirm it. The problem was that the evidence was not going to come from anywhere obvious. It was not going to come from further study of the continents, from more fossil comparisons or more refined measurements of coastline geometry. It was going to come from somewhere unexpected, from an instrument designed for a completely different purpose, from a war. Holmes published the idea carefully, almost reluctantly, in the way of a man who knew he was going further than his evidence could carry him. The 1944 edition of Principles of Physical Geology laid it out with the precision and the hedging of a scientist who understood exactly where certainty ended and speculation began. The convection currents he described were driven by heat rising from within the mantle, heat produced not by any mysterious primordial fire left over from the Earth's formation, but by the decay of radioactive elements, uranium, thorium, potassium, buried in the rock itself, generating warmth the way a compost heap generates warmth, slowly, invisibly, from chemical transformation happening at the atomic level. The rock was its own furnace. It had been burning in this quiet way for billions of years. And here it is worth pausing on that phrase, billions of years, because the number matters enormously, and Holmes himself had helped establish just how enormous it was. Before the development of radiometric dating, before Holmes and others worked out how to read the decay of one element into another as a clock, the age of the Earth was genuinely uncertain. There were estimates based on the rate of erosion, on the salinity of the oceans, on the cooling of a once molten sphere, and they varied wildly. Some put the Earth at tens of millions of years, some at a few hundred million. But uranium decaying into lead does so at a fixed and measurable rate, the same rate in every rock on every continent, undisturbed by pressure or temperature or time, and when Holmes applied that clock to ancient rocks, he found ages that pointed towards something on the order of 4.5 billion years. The planet was almost incomprehensibly old, older than anyone had been quite willing to believe. This mattered to the drift debate in a way that is easy to overlook. One of the quiet objections to continental drift, never quite stated as loudly, as the missing mechanism problem, but always present at the edge of the argument, was a question of time. If the continents had moved from a single supercontinent to their present positions, they had moved enormous distances, thousands of kilometers, and they had moved at rates so slow as to be essentially undetectable by any instrument available to science. For that journey to be possible at all, there had to be enough time. And 4.5 billion years is enough time. Moving at a few centimeters per year, the rate the plates would eventually be measured at, a continent could cross an ocean in 100 million years. 100 million years sounds impossibly long, but set against 4.5 billion, it is a fraction of a working morning. The deep time that Holmes helped measure was the room the whole theory needed. Without it, drift was geometrically implausible, even if you believed the idea. With it, drift was not only possible, but almost inevitable. Holmes gave the theory two things then. He gave it time, the deep time established by uranium-lead dating, the 4.5 billion year canvas on which continents could wander. And he gave it a candidate engine, the thermal convection currents rising and falling in the mantle, driven by radioactive heat, vast and slow and invisible, turning over on timescales that made human civilization look like a single breath. Neither gift was proven. The convection currents were theoretical. The radiometric dates were real and solid, but they did not by themselves confirm that anything had moved. What Holmes had done was clear the terrain. He had shown that drift was physically possible, given enough time and a plausible mechanism, in a way that Wegener's own proposals had never managed to do. But clearing the terrain was not the same as winning the argument. Through the 1930s and 1940s, through the war and the years immediately after it, the geological community remained divided and largely skeptical. Jeffries had not changed his mind. The American school, influential and well-funded, tended toward what they called the permanence of the ocean basins. The idea that the continents had always sat more or less where they sat now, and that the fossils and the coastlines were explained by land bridges, long sunken connections between the continents that animals and plants had once crossed and that had since subsided into the sea. This was, as it turned out, entirely wrong, but it was not a foolish idea. It preserved the rigid Earth that Jeffries's physics demanded. It offered an explanation for the fossils. It did not require you to believe that enormous masses of continental rock had somehow slid thousands of kilometers across the face of the planet. And in the absence of direct evidence for drift, it was the conservative and defensible position. The evidence that would break the deadlock was not going to come from any of the places either side was looking. It was not going to come from more fossil work, from more coastline geometry, from a better theory of mantle convection, from any further refinement of the radiometric timescale. It was going to come from the ocean floor. And the ocean floor was, in the 1940s, almost entirely unexplored. It was the largest and least known surface on the planet, hidden under kilometers of salt water, impossible to examine directly, visited only in the most superficial way by the lead lines and dredges of 19th century oceanography. Nobody knew what was down there. And one of the reasons nobody knew was that until the war there had been very little reason and very little money to find out. The war changed that. In the early 1940s, the most pressing navigational and strategic problem facing the Allied navies was the German submarine. The U-boat was hunting Allied shipping across the Atlantic with devastating efficiency, and the question of how to find a submarine, a small metal object lying still or moving slowly in 3 dimensions of dark water, was not a simple one. Sound was one answer, and sonar developed rapidly during the war. But magnetic anomaly detection was another. A steel submarine, even lying still on the seafloor, disturbs the local magnetic field. If you tow a sensitive magnetometer, an instrument that measures the strength and direction of the magnetic field, at the right depth and with the right precision, you can detect that disturbance. The magnetometer becomes a kind of sensor for hidden metal in the water below, and so the Allied navies began developing magnetometers that could be towed behind ships and aircraft, dragged across the ocean in search of submarines, reading the faint variations in the magnetic field that might reveal something hiding beneath the surface. The submarines were there, and the magnetometers found some of them, but the magnetometers also found something else. Something in the data that was not submarines at all, that was not any piece of metal dropped or sunk by human hands, but was instead a pattern in the rock itself, a variation in the magnetic field of the ocean floor. Faint, systematic, extending over enormous areas. The officers and analysts who saw it noted it, filed it, and moved on. They were fighting a war. The strange magnetic pattern in the open ocean was not their problem. But after the war, the instruments and the knowledge of how to use them persisted. The Cold War succeeded the Second World War with barely a pause, and the strategic imperatives barely changed. The Soviet submarine fleet was growing. The need to monitor, map, and understand the ocean floor, to know where submarines could hide, how the water moved, what the magnetic environment looked like at depth, remained urgent and extremely well-funded. The United States Office of Naval Research poured money into oceanographic research through the 1950s, much of it directed toward what sounded like pure science, but was always somewhere beneath the surface, connected to the practical question of finding submarines and understanding the ocean they moved through. The ships went out, the magnetometers trailed behind them on long cables, and the ocean floor began, very slowly, to give up its secrets. It was in this context, in this strange overlap between Cold War military necessity and genuine scientific curiosity, that Marie Tharp sat in her office at Columbia University's Lamont Geological Observatory on the Hudson River in New York and began to draw a map. Tharp was a scientist at Lamont, working with the oceanographer Bruce Heason, and her job was to take the depth soundings coming in from survey ships and translate them into a picture of what the ocean floor actually looked like. This was painstaking and demanding work. The soundings came in as numbers, depths at particular positions, and turning a grid of numbers into a coherent map of a hidden landscape required both rigorous method and a kind of spatial imagination, the ability to see the shape of a thing from a scatter of isolated measurements, the way a sculptor might see the form waiting inside the stone. Through the early and middle 1950s, Tharp worked at this. The data accumulated, the map grew, and something began to emerge from it that had not been expected, that did not fit the received picture of a smooth and featureless ocean bottom. Running down the center of the Atlantic Ocean, following the line of the Mid-Atlantic Ridge, the great underwater mountain range that sailors had known vaguely about since the 19th century but had never mapped in detail, there was a valley, a deep, narrow, steep-sided rift valley running along the very crest of the ridge like a groove cut down the center of a raised seam. Not a gentle depression in the seafloor, but a genuine rift, kilometers deep, with walls rising sharply on either side. Tharp knew what a rift valley meant. Rift valleys form where the crust is being pulled apart, where the ground is being stretched and thinned, where rock on either side is moving in opposite directions. The East African Rift Valley on land was a known and studied feature, and it was understood to be a place where Africa was being pulled apart along a seam. If there was a rift valley running down the center of the Mid-Atlantic Ridge, then the Mid-Atlantic Ridge was also a place where the crust was being pulled apart, where new material was being added, where the ocean floor on either side of the ridge was moving away from the center. She brought this interpretation to Heason, and Heason, a man of considerable ability and considerable stubbornness, told her that it was girl talk, that the interpretation was wrong, that the data did not say what she thought it said. The precise phrase he used, girl talks, appears in the record, and it has the quality of a casually delivered dismissal the kind that arrives so quickly and with such confidence that the person on the receiving end is expected simply to accept it and move on. Tharp did not move on. She went back to the data and looked at it again. She refined the map. The Rift Valley remained. It remained, moreover, entirely consistent with something else Tharp had noticed in the data. Running along the line of the mid-Atlantic ridge, concentrating in a way that was too systematic to be random, were earthquakes. Small earthquakes mostly, not the great catastrophic events that occasionally made headlines, but a continuous low-level seismic activity distributed along the ridge axis in a pattern that matched the Rift Valley almost exactly. And earthquakes, like rift valleys, are what you get when rock is moving, when the ground is under stress, when something is being torn apart or pushed together or sliding past itself. The map and the earthquake distribution together told a coherent story. The Mid-Atlantic Ridge was not just a mountain range on the ocean floor. It was an active feature, a seam where the floor was being pulled apart, where new rock was being added to either side, where the Atlantic Ocean was, in some sense, being made. The continents on either side of the Atlantic were not fixed. They were being pushed apart. But Heisen did not want to hear this, at least not initially. The Rift Valley result was eventually published, and it was eventually taken seriously, and Heisen himself would later come around to a version of the expanding seafloor idea. But in the 1950s, when the data was first coming in, the interpretation was contested, and the person who had actually seen it in the numbers was not given the credit she deserved with anything like the promptness it warranted. The ridge itself was extraordinary, independent of any interpretation. The Mid-Atlantic Ridge is the longest mountain range on Earth, not the longest above water. The Andes and the Himalayas are the great above-water ranges, but the longest on the planet, period. It runs for approximately 65,000 kilometers, winding through every ocean basin, tracing a rough line down the middle of the Atlantic, from Iceland in the north to the southern tip of the ocean, curling around the bottom of Africa, extending into the Indian Ocean, threading through the Pacific, a continuous volcanic seam following the curvature of the Earth. 65,000 kilometers is roughly 1.5 times the circumference of the Earth itself. The whole thing is almost entirely underwater, hidden beneath kilometers of ocean, visited by almost no human being, unknown to almost all human history before the 20th century. It is in many respects the most significant topographic feature on the planet, and most people have never heard of it. The ridge is not just large, it is active. Along its entire length, along this 65,000 kilometer seam, molten rock rises from below, erupts onto the ocean floor, cools, solidifies, and is pushed to either side as more molten rock rises behind it. The ridge is a factory continuously producing new ocean floor, adding it symmetrically to either side, building the ocean basins one thin layer of fresh basalt at a time. The process is slow enough that it is entirely invisible on any timescale a human being can observe directly. But it is relentless, and over the hundreds of millions of years that the Atlantic has existed, it has built an entire ocean basin from essentially nothing. Harry Hess had spent part of the Second World War aboard a United States Navy ship, and he had used the time well. As a Navy captain in the Pacific, Hess had run the echo sounding equipment essentially continuously, mapping the sea floor beneath him as the ship moved on its military business. Echo sounding works by sending a pulse of sound down into the water and listening for the echo. The time the echo takes to return tells you how deep the water is, and a careful record of those depths as you move across the ocean produces a profile of the bottom beneath you. Hess accumulated an enormous amount of this data during the war, and what it showed him was a sea floor more complex and more varied than the smooth, featureless plain that most geologists had imagined. There were mountains, valleys, flat-topped seamounts that he named guyots, trenches of extraordinary depth. The ocean floor was a landscape, and it was not passive. After the war, Hess continued to think about what the ocean floor was telling him. He thought about the mid-ocean ridges and the trenches. He thought about the heat flow measurements coming in from oceanographic surveys. The ocean floor near the ridges was measurably warmer than the ocean floor far from them, which was exactly what you would expect if hot material was rising from below at the ridge axis. He thought about the sediments, and specifically about the fact that the sediments on the ocean floor near the ridges were thin and young, while the sediments farther from the ridges were older and thicker, as if the rock near the ridges had not existed for very long, as if it had been recently made. He put it all together, and in 1962 he published a paper that would change everything. He called it, in a phrase that has stayed in the literature ever since, an essay in geopoetry. He used that phrase in the paper itself to acknowledge that what he was offering was not yet a fully proven argument, that it was a picture of the world, a way of understanding the ocean floor that was guided as much by the logic and aesthetics of a coherent story as by the hard, incontrovertible numbers. It was, he said, geopoetry. And then he described seafloor spreading. The idea was this: hot material rises from the mantle at the mid-ocean ridges. It erupts as basalt, adding new rock to either side of the ridge axis. The new rock is then pushed outward, away from the ridge, as more new rock is added behind it, in the way that items on a conveyor belt are pushed along as more items are added at the feeding end. The ocean floor does not stay where it is made. It moves, spreading away from the ridge, crossing the ocean floor over millions of years until it reaches the far edge of the ocean basin. And there, at the deep ocean trenches, the deepest places on Earth, the Mariana Trench and its kind, it plunges back down into the mantle. The old, cold, dense oceanic crust descends into the hot rock below, recycled, destroyed, melted, and remade over millions of years. The ocean floor is a conveyor belt. It is made at the ridge, spreads across the ocean, and is consumed at the trench. It is never more than a few 100 million years old because it is continuously recycled. And the continents? The continents are passengers. They ride on top of the conveyor belt carried by the motion of the ocean floor beneath them, but they are not themselves consumed at the trenches because continental rock, the lighter granitic material that Wegener had described as floating on the denser mantle, is too buoyant to sink. When the conveyor belt reaches the trench and begins to descend, the continent simply stays at the surface, crumpling at its leading edge as the dense oceanic crust dives beneath it, building mountain ranges from the compression. The continents are not ploughing through the ocean floor, they are riding on it, and the ocean floor is moving. This was a beautiful idea. It resolved with a single picture the problem that had plagued Wegener's theory from the beginning. Wegener had imagined the continents moving through the oceanic crust, pushing through it like ships through water, and Jeffries had correctly pointed out that this was physically impossible. The oceanic crust was rock, rigid rock, and no force Wegener could name was strong enough to drive a continent through it. Hess's picture was entirely different. The continents were not moving through the ocean floor was moving, and the continents were carried along. The force required was not the force to push a continent through rock, but the force to move the entire ocean floor. A very different problem, and one that the thermal convection currents Holmes had described could plausibly supply. The passengers do not need to push. They only need to ride. But the idea was still, in 1962, an essay in geopoetry. Hess himself had said so. It was coherent, it was physically plausible, it resolved the mechanism problem, and it explained the pattern of sediments and heat flow on the ocean floor. But it was not proven. There was no direct, incontrovertible evidence that the ocean floor was actually spreading, that new crust was actually being added at the ridge axis, that the pattern Hess described was real and not just an elegant story built on suggestive data. To prove that, you needed something else, something that left a clear and unambiguous record, something that could be read like a document, something that said, not just this is consistent with spreading, but this could only have happened if spreading occurred. The ocean floor had been keeping exactly that record all along, in the magnetic properties of the rock itself, in a signal that no one had understood, in measurements that had been accumulating in the files of naval surveys for a decade, waiting for someone to read them correctly. The magnetometers trailing behind the survey ships had not been idle. They had been recording continuously the strength and direction of the local magnetic field at the ocean surface, and the data showed something unmistakable once you knew how to look at it. The magnetic field over the ocean floor was not uniform. It varied, in bands, in stripes, alternating zones of slightly stronger and slightly weaker magnetic signal, running parallel to the mid-ocean ridges extending for hundreds of kilometers on either side. The stripes were there in data from the Atlantic, the Pacific, the Indian Ocean. They were real, and they were very strange. What were they? Why would the magnetic field over the ocean floor vary in this regular, striped pattern? The surveys had noted the anomalies, the word used in the scientific literature for these deviations from the expected average, and had filed them away, and for years nobody had a satisfying explanation for what they meant. They did not fit any simple geological model. They were too large to be caused by local variations in the composition of the seafloor rock. They were too regular to be random. They extended too far and were too consistent to be noise. They were real and they were saying something and nobody knew what. The answer came in 1963 from a pair of researchers at Cambridge University. Fred Vine was a graduate student and Drummond Matthews was his supervisor, and what they proposed in a paper that year was simultaneously simple and staggering. The ocean floor is made of basalt. Basalt contains magnetite, a mineral with a name that means what it says. A mineral that is magnetic, that aligns itself with the Earth's magnetic field as it cools from the molten state, the way iron filings align themselves with the field of a magnet. When basalt erupts at the mid-ocean ridge and cools, the magnetite crystals in it freeze in place, locked into whatever direction the Earth's magnetic field is pointing at that moment. The rock becomes in that instant a permanent record of the field as it was when the rock solidified, a compass needle fixed forever in the stone. Now, the Earth's magnetic field reverses. It has done so repeatedly throughout geological history, at irregular intervals, the north and south magnetic poles swapping positions in a process that takes thousands of years and leaves behind a record in any rock that solidified during or after the reversal. Sometimes the field points the way it does now, the configuration called normal, in which a compass points roughly toward geographic north, and sometimes it points the other way, reversed, the configuration in which a compass would point south. The reversals are well documented in rocks on land. Geologists had been mapping them for years before anyone applied the same thinking to the ocean floor. And here was what Vine and Matthews saw. If the seafloor is spreading, if new rock is being continuously added at the ridge axis and pushed outward, then the rock being added carries with it the imprint of the magnetic field as it was when that particular parcel of rock solidified. Normal field, reversed field, normal, reversed. In whatever sequence the field happened to reverse, over the millions of years the spreading was occurring. And because the spreading happens symmetrically, because new rock is pushed outward in both directions from the ridge axis at the same rate, the record on one side of the ridge is a mirror image of the record on the other side. The same sequence of normal and reversed bands in the same order, at the same distances from the ridge on both sides, symmetrically, like a barcode that reads the same whether you hold it one way or the other. That is what the magnetic stripes were. That was their meaning. They were the tape recording the ocean floor had been making of Earth's flipping magnetic field, laid down stripe by stripe as the seafloor spread, symmetric across the ridge axis because the spreading itself was symmetric. And the symmetry was the proof. There is no other process, no other geological mechanism that produces a pattern like that. A symmetric barcode of magnetic reversals mirroring itself across the length of a mid-ocean ridge can only be produced by one thing: continuous creation of new crust at the ridge axis, spreading outward in both directions, recording the field as it goes. The geopoetry in that moment became geology. Lawrence Morley, a Canadian geophysicist, had arrived at the same conclusion independently, working from the same data, and had written a paper describing it before Vine and Matthews published. His paper was rejected by 2 journals in succession, one editor remarking that the idea might make interesting discussion at a cocktail party, but was not suited to a serious scientific publication. Morley's paper was never formally published in the way the Vine-Matthews paper was. The hypothesis bears 3 names nonetheless: the Vine-Matthews-Morley hypothesis, because the scientific community came eventually to understand that Morley had seen it first and been turned away. The story of Morley's rejections has a particular resonance in the history of this idea, the idea that kept being turned away before the world was ready for it. But the data was there, the stripes were there. And once Vine and Matthews had explained them, others could see it too. The surveys accumulated, ship after ship, trailing its magnetometer through the ocean, reading the barcode on the seafloor. The pattern repeated, ocean after ocean, ridge after ridge. The symmetry was everywhere. And with the symmetry came something else: a clock. Because the magnetic reversals were also recorded in rocks on land, in sequences that geologists had been dating radiometrically, it was possible to match the pattern of reversals in the seafloor stripes to the known sequence of reversals through geological time. This stripe corresponds to this reversal, which happened this many millions of years ago, which means this rock was here at the ridge axis this many millions of years ago, which means the seafloor has been spreading at this rate. The ocean floor became a calendar of its own motion, written in the language of magnetism, stretching back 200 million years, at the age of the oldest seafloor, the time at which the Atlantic began to open. And the continents on either side of the Atlantic were, in that reckoning, the shores of a rift that had been widening for 200 million years. Wegener's picture was not just plausible anymore, it was measurable, it was dated, it was real. The data poured in through the late 1950s and early 1960s, and it brought other confirmations along with it. The measurements of heat flow at the ridge were consistent with the model. The seafloor near the ridge is warmer because hot mantle material is closer to the surface there. The sediments thickened as you moved away from the ridge, as expected if the rock near the ridge was young and the rock far from it had had more time to accumulate sediment. The ages of the rocks on the ocean floor where they could be sampled and dated were youngest near the ridge and progressively older farther away. Again, exactly as the spreading model predicted. No single piece of evidence was decisive on its own, but together they composed something close to a proof, the kind of convergent evidence from independent sources that science considers as trustworthy as it gets. And then there was what was happening beneath the ocean floor at the other end of the conveyor belt, the trenches, the places where the old, cold, dense oceanic crust was plunging back into the mantle. Subduction. The word comes from the Latin for leading under, and it describes exactly what happens. One plate is led under another, diving at an angle into the mantle, dragging its leading edge down into the hot rock below. The descending plate carries water with it, water trapped in cracks in the rock and bound into minerals. And as the plate heats and the pressure increases, the water is released into the mantle rock above, lowering its melting point and generating magma. That magma rises, and where it reaches the surface it builds volcanoes. The chain of volcanoes running along the edge of a subducting plate, the Ring of Fire around the Pacific, the volcanic arcs of the Andes and the Cascades, is the surface expression of this process of water-charged magma rising from a plate being dragged downward into the deep. The subducting plate also generates earthquakes. As it descends, it does not slide smoothly. It jerks, it sticks, it breaks, and each break is an earthquake. The earthquakes cluster along the inclined plane of the descending plate, deepening as you move toward the subduction zone, and then deeper still as you follow the plate underground. This pattern had been identified by Kyu Wadati in Japan in the 1920s and further developed by Hugo Benioff in the United States in the 1940s and 1950s. The inclined zone of deep earthquakes that bears both their names, the Wadati-Benioff zone. At the time of its discovery, the pattern was real but unexplained. There was no framework in which it made sense. Once the spreading model was in place, the Wadati-Benioff zone became a direct image of subduction, a seismic portrait of a plate descending into the mantle, its earthquakes marking its path downward the way lights mark the descent of a ship into deep water. Everything was connecting: the ridges, the stripes, the trenches, the earthquake zones, the volcanoes, all of them aspects of the same process, all of them explicable within the same picture of ocean floor being made at one end and consumed at the other, continents riding as passengers on the moving plates, carried apart and pushed together and rotated over the immensity of geological time. The picture was becoming a theory, a real theory in the scientific sense, not a guess, not a conjecture, but a framework of ideas so broadly supported by independent evidence, so capable of explaining so many different things, that to abandon it would require abandoning an enormous amount of verified observation. And in those same years, one more piece fell into place. One more observation from a geologist of extraordinary imagination that showed how the system worked not just at ridges and trenches, but at a third kind of boundary. J. Tuzo Wilson, a Canadian geophysicist, was looking at the pattern of earthquakes along the ocean floor and at the way the mid-ocean ridges were arranged. The ridges were not smooth, continuous lines. They were offset. The mid-Atlantic ridge, for example, is cut again and again by fracture zones, breaks in the crust running perpendicular to the ridge axis, along which the two halves of the ridge are displaced sideways relative to each other, like a stick that has been snapped and the two ends pushed past each other. These fracture zones had been mapped and were clearly real, but their behavior was puzzling. The earthquakes along them clustered not along the full length of the fracture zone, but only between the two offset sections of ridge, the active segment, where the two sides were actually sliding past each other. Beyond the ridges, the fracture zone continued, but was seismically quiet. Wilson understood what this meant. The fracture zone beyond the ridge was not active because the rock on either side of it was moving in the same direction. It was old seafloor spreading away from the ridge, and on both sides of the fracture zone, the old seafloor was moving the same way, away from the ridge axis. Only in the segment between the two ridge sections were the rocks on either side moving in opposite directions, and only there were earthquakes produced. This was a new kind of plate boundary, one where the plates were neither colliding nor spreading apart, but sliding sideways past each other. Wilson called it a transform fault. It was the third type of boundary: ridge, trench, transform. And the three types together accounted for all the places in the world where tectonic activity was concentrated. Wilson was also the scientist who most clearly articulated what a fixed mantle hotspot could do to a moving plate. The Hawaiian Islands are a string of islands and seamounts extending across the Pacific in a chain that progressively ages toward the northwest. The big island of Hawaii, youngest and most volcanically active, at the southeastern end. a long line of older, smaller, more eroded islands and submerged seamounts extending northwest, getting older as you go, until the chain bends and continues in a different direction as the Emperor seamounts, angling away toward the Aleutian Trench. The bend in the chain is sharp and distinctive. Wilson's insight was that the chain was produced not by a moving source of heat, but by a fixed one. A hotspot anchored deep in the mantle, punching magma up through the moving plate above it, creating a new volcanic island wherever the plate carried fresh rock over it, while the old volcanic islands were carried away from the hotspot and slowly died, eroded, and subsided beneath the sea. The chain is the track of the plate passing over the hotspot, and the bend in the chain is a change in the direction of the plate's motion. A turn in the conveyor belt's path that happened roughly 47 million years ago, recorded permanently in the geometry of the islands and seamounts that trace its journey across the Pacific. Here was an independent clock and a record of plate motion entirely separate from the magnetic stripes. The Hawaiian chain said, "This plate has been moving in this direction at a measurable speed for tens of millions of years, and before that, it moved in a different direction." The geometry of the chain was the record of motion, written in the size and age and position of extinct volcanoes, stretching back deep into geological time. And now, with the pieces of the machinery beginning to assemble themselves, the question that had haunted geology for half a century was finally being answered, not through argument, but through evidence. Not through the force of a single persuasive voice, but through instruments reading what the planet had already written down in the dark, in the deep cold of the ocean floor, long before any human being thought to ask. The magnetic stripes were the key, and to understand why they were so decisive, why they silenced the remaining objections in a way that no amount of fossil comparison or coastline matching ever could, you need to hold one fact in mind, a fact about the Earth itself that had been established by the time Fred Vine and Drummond Matthews sat down to write their paper in Cambridge in 1963. The Earth's magnetic field reverses, the north magnetic pole becomes south, and the south becomes north at irregular intervals, not on a schedule you could set a clock by, but on a geological rhythm of hundreds of thousands to millions of years. This has been happening throughout Earth's history, flip after flip, a slow oscillation in the planet's magnetic personality that leaves no outward sign in daily life, no change in the color of the sky or the temperature of the air. The compass simply points the other way, and then after some span of geological time, it points back again. Now consider what happens at a mid-ocean ridge, one of those volcanic seams running down the center of an ocean basin, where new rock is being born continuously. Molten basalt wells up from below, breaks through the ocean floor, and flows out into water so cold it solidifies quickly, becoming new crust. And within that cooling rock, something precise and permanent is happening, tiny crystals of a mineral called magnetite. The same mineral that makes certain stones naturally magnetic, the same mineral that ancient navigators recognized in lodestone, are locking themselves into alignment with the Earth's magnetic field at the moment of cooling. They are like compass needles frozen permanently in position as the rock sets hard around them. Each ribbon of new crust as it cools is a snapshot of the Earth's field direction at that moment in geological time, and because the ridge pushes the crust outward symmetrically on both sides, new rock forming at the center, older rock carried away equally in both directions, like two conveyor belts running in opposite directions from the same assembly line. The record of those field reversals is preserved in parallel stripes running along both flanks of the ridge. A stripe of normal polarity, magnetic north, pointing roughly where our compasses point today, sits beside a stripe of reversed polarity, and beside that another normal stripe, and so on outward from the ridge in both directions, a barcode of magnetic history spreading across the ocean floor, mirror-symmetric on each side of the volcanic seam at the center. When a ship with a magnetometer towed behind it, one of those submarine hunting instruments repurposed now for oceanographic surveys, crossed over one of these stripes, the instrument registered an anomaly, a measurable departure from the expected background field. The rock beneath was adding its own magnetic signature to the Earth's ambient field, or subtracting from it, depending on whether its magnetite crystals were aligned with the current field or against it. On a chart, these anomalies plotted as peaks and troughs, a repeating pattern striped like a barcode laid across the ocean floor. What Vine and Matthews recognized, and what Lawrence Morley in Canada recognized independently at almost the same time, was the full implication of that pattern. The symmetry was the proof. Both flanks of the ridge showed the same pattern of stripes, mirrored perfectly on each side of the central volcanic axis. That symmetry could only arise if new crust was being created continuously at the ridge and pushed outward in both directions. The stripes were a record of time, running outward from the center. The rocks nearest the ridge were youngest, the rocks farthest away were oldest, and the magnetic barcode across the floor was the planet's own record of the history of its field reversals, written in the cooling rock, preserved in the dark under kilometers of ocean. This was the tape recorder Hess had implied when he called sea floor spreading an essay in geopoetry. It turned out the ocean floor was not just a conveyor belt, it was a continuous archive, a running record of the Earth's magnetic history pressed into stone, laid out in readable order, waiting for an instrument sensitive enough to detect it and a mind ready to ask the right question. Vine was 23 years old when he worked out what the anomalies meant. Matthews was his supervisor, and Morley, writing up the same insight on the other side of the Atlantic, sent his paper to the journal Nature and to the Journal of Geophysical Research and was rejected by both before Vine and Matthews published. Morley's referees, apparently finding the idea too speculative, too large a claim to rest on patterns read from a magnetometer towed behind a ship. The idea that the ocean floor was a tape recorder of planetary history struck some careful scientists as going further than the data warranted. It did not go further than the data warranted. Within a few years of the 1963 publication, as more surveys mapped more of the ocean floor, as the barcode patterns were found not just in the Atlantic, but in the Pacific and the Indian Ocean, as the chronology of magnetic reversals was established independently from measurements of volcanic rocks on land, and as the ages of the stripes were found to match that chronology with striking precision, the case became essentially irresistible. The ocean floor was spreading. The crust was new at the ridges and old at the margins, exactly as Hess had proposed. The magnetic stripes were not an anomaly to be explained away. They were the signal. The proof that Wegener had never found, and that Arthur Holmes had argued for without evidence, and that a generation of skeptical physicists had correctly demanded, was finally, undeniably there. Written in magnetite crystals, read by instruments designed to hunt submarines, and interpreted by a young Cambridge geophysicist and his supervisor in a paper that opened one of the final chapters in the transformation of geology. The field had been waiting, in a sense, for precisely this. Not for a more eloquent argument in favor of drifting continents, not for a more impressive jigsaw fit or a longer list of matching fossils. What it needed was mechanism, and what the magnetic stripes provided was not just evidence for spreading, but the very process that revealed the engine. The ocean floor was moving because it was being made. New rock was being created at the ridge and pushed outward, and old rock was being destroyed at the far margins, sinking back into the mantle. The machine was visible. The proof was in the barcode. And around that proof, in the years between 1965 and 1968, the framework of plate tectonics assembled itself with remarkable speed. The pieces had been waiting separately: the magnetic stripes, the seafloor spreading hypothesis, the deep earthquake zones, the evidence for a globe-spanning ridge system, and now they clicked together into a single coherent picture of how the Earth worked. J. Tuzo Wilson, the Canadian geophysicist who had already identified the Hawaiian hotspot mechanism, made another crucial contribution. He recognized a type of geological boundary that had puzzled geologists, a fault where two sections of crust slide horizontally past each other, neither spreading nor subducting, simply sliding. He called it a transform fault. The San Andreas Fault in California is one of the most famous examples, not a place where the Pacific Plate is diving beneath North America, but a place where it is sliding northward past it, locked and grinding and releasing in earthquakes. Wilson's recognition that transform faults were the third type of plate boundary, alongside spreading ridges and subduction zones, completed the geometry. A closed, consistent system emerged. Plates form at ridges, move outward, slide past each other at transform faults, and disappear back into the mantle at subduction zones. The surface of the Earth is a set of rigid plates moving against each other in a small number of distinct ways, and all the geological activity, the earthquakes, the volcanoes, the mountain ranges, occurs at the places where plates meet. The subduction zones had their own independent line of evidence, one that had been building for years before the full synthesis came together. Kyu Wadati, a Japanese seismologist, had noticed in the 1930s that deep earthquakes occurring not near the surface but at depths of hundreds of kilometers, clustered along inclined planes dipping steeply into the earth beneath certain coastlines and island arcs. Hugo Benioff, an American seismologist, mapped these deep earthquake zones more extensively in the 1950s. What came to be called the Wadati-Benioff zone is now understood as the seismic signature of a subducting plate, the cold, rigid slab of oceanic crust descending into the mantle and breaking as it goes, releasing the stored elastic energy of its deformation as earthquakes. The deepest earthquakes in the world occur in the Wadati-Benioff zones of the Western Pacific, at depths where the material has descended 300 or 400 kilometers into the Earth. They are the sound of a plate being swallowed. Dan Mackenzie and Robert Parker formalized the geometry in 1967, describing the motions of the plates as rotations on a sphere, each plate moving as if rotating about a fixed axis. What geometers call an Euler rotation, the same mathematics that describes the spinning of a top or the tilting of a gyroscope, applied now to the slow turning of lithospheric plates across the surface of the globe. Jason Morgan at Princeton extended the analysis in 1968, describing the Earth's surface as divided into a small number of rigid plates, each moving according to its own Euler rotation, and identifying the boundaries between them as the places of geological activity. The mathematical framework was elegant and precise, and it matched the data from seismology, from marine magnetic surveys, from the geometry of fracture zones on the ocean floor. The rigid Earth objection that Harold Jeffreys had raised with such mathematical force, the objection that had been physically sound, correctly argued, and ultimately immovable to Jeffreys himself, was not refuted so much as dissolved by a distinction. The lithosphere, the rigid outer shell of the Earth comprising the crust and the topmost part of the mantle, is indeed rigid, on the timescales relevant to everyday experience and to the engineering calculations Jeffreys had made. But beneath it lies the asthenosphere, a hotter, weaker zone of the mantle where the rock, under sustained pressure and at elevated temperature, behaves not as a rigid solid, but as an enormously viscous fluid capable of flowing on geological timescales, of deforming and moving in response to the forces acting upon it. Think of the way glass flows imperceptibly slowly in the panes of very old windows, or the way a glacier moves, solid to the touch, but flowing under its own enormous weight over centuries and millennia. The asthenosphere flows in something like that fashion, but on a far vaster scale and over far longer times. The rigid plate floats on this plastic layer, and it is the plasticity of the asthenosphere that allows the plates to move. Jeffries had been calculating whether solid rock of the Earth's bulk could deform in the way continental drift required, and his answer was correct. Solid rock of that kind cannot deform fast enough. But the Earth is not uniformly solid rock. It has a rigid outer layer and a plastic inner layer, and the rigid outer layer does not deform. It moves as a coherent slab, riding on the deformable material beneath it. The distinction between lithosphere and asthenosphere was the key that Jeffries's formulation had missed, not because he was a poor physicist, but because the evidence for the distinction had not yet been gathered. His physics was correct. The premise, a uniformly rigid Earth, was what the ocean floor surveys eventually refuted. He was never persuaded. He died in 1989, nearly 30 years after the seafloor spreading evidence had convinced almost everyone else in the field, still holding to his view that the data were insufficient and the mechanism inadequate. He was a rigorous man, and rigor is not always the same thing as flexibility. With the mechanism named and the mathematics formalized, the answer to the question that had killed Wegener's theory could finally be stated clearly. The force that moves the plates, the engine Wegener could not produce, and that his critics correctly demanded, is primarily slab pull. When a plate is old and cold and dense, and its leading edge is pushed against or beneath another plate at a subduction zone, gravity does the rest. The cold oceanic crust is denser than the warm mantle rock beneath it, and so it sinks, and as it sinks it pulls the rest of the plate behind it, the way a heavy tablecloth draped over the edge of a table pulls the rest of the cloth across the surface. That pull is slab pull, and it is the dominant force. The ridge push contributes as well. The elevated mid-ocean ridge is warm and buoyant, and plates slide gravitationally away from it, pushed by the gentle downhill slope from the ridge toward the deeper ocean floor, as if sliding slowly off a long, broad hill. And all of this operates within the context of mantle convection. The large-scale circulation of the mantle itself, driven by heat flowing outward from the Earth's interior, heat generated by the slow decay of radioactive elements, the very mechanism that Arthur Holmes had proposed in the late 1920s and set down in his textbook in 1944. Holmes had been right about the engine. He had simply had no way to prove it. Now the proof surrounded it from all directions: the stripes, the subduction zones, the ridge geometry, the seismology, the heat flow measurements. And the engine had a name and a quantified mechanism. The wound that the theory had carried since 1912, the open question that had killed the patient in the eyes of every rigorous physicist who examined it, was closed. The engine was slab pull and ridge push operating within mantle convection. The machine had been running for billions of years under everyone's feet, and now it had a face. You can measure it? That is perhaps the most quietly astonishing thing about where the science eventually arrived. You can sit at a desk and look at the data from a network of GPS receivers distributed around the globe and watch the plates move. Not metaphorically watch, not infer from indirect evidence, but directly measure the positions of points on different plates and see them diverging or converging at rates of centimeters per year. The Atlantic is widening at roughly 2 to 2.5 centimeters per year. About the rate your fingernails grow, that image that keeps recurring because nothing else in ordinary experience captures the right combination of real and imperceptible. The fastest boundaries in the Pacific between the Nazca Plate and the Pacific Plate move at more than 10 centimeters per year. The Indian Plate is still driving northward into Asia, carrying the weight of a subcontinent, pushing the Himalayas higher by a few millimeters per year. The Himalayas and Mount Everest at their highest point are themselves a demonstration of the theory's unifying power. Near the summit of Everest, in the limestone and sedimentary rock of the highest mountains on Earth, there are marine fossils, the shells and traces of sea creatures that lived in a warm, shallow ocean that existed where the Himalayas now stand before India collided with Asia roughly 50 million years ago. The collision closed that ocean, compressed its seafloor sediments, and drove them upward, kilometer after kilometer of uplift, continuing to this day as India keeps moving north. The roof of the world is built partly from the bottom of the sea. There is no more vivid demonstration available of what the theory means. A sea creature dies in warm water in a shallow tropical ocean, sinks to the sediment, is slowly fossilized, and then, over tens of millions of years, is carried slowly upward by the force of a continental collision until it rests almost 9 kilometers above sea level, inside a rock face near the highest point the surface of the Earth reaches. The theory is not abstract. It is written in limestone at altitude in fossils. The ring of fire around the Pacific is another expression of the same mechanics. The Pacific Plate and the many smaller plates surrounding it are all, at their margins, diving beneath the continents and island chains that ring the Pacific Basin. And at every place where an oceanic plate subducts beneath another plate, volcanoes form above it. The descending slab carries water locked into its minerals, water that lowers the melting point of the mantle rocks above the slab, causing them to melt, generating magma that rises through the overlying plate and erupts at the surface. The ring of fire, that horseshoe of volcanic peaks and earthquake zones encircling the Pacific, is the surface expression of subduction happening all the way around the basin. Roughly 3/4 of the world's active volcanoes are found along it. Roughly 9 in every 10 earthquakes measured on the planet occur along it, or along the other subduction zones, and transform boundaries of the global plate system. The violence of the Earth's surface, the shaking of the ground, and the eruption of fire from mountains is not random. It is the sound and fury of plates grinding against each other at their margins, the noise the machine makes as it runs. And the machine is not static. It is creating new geology right now in places you could visit and observe. In East Africa, a long fracture is developing, the East African Rift, sometimes called the Great Rift Valley, where the African continent is being pulled apart along a seam, a new divergent boundary forming in the middle of a landmass. The process is slow by human standards, a few millimeters per year in most places, but the evidence is there. Long, deep lakes filling the widening valley, volcanoes along its flanks, earthquakes rattling the rift walls. This is what a young ocean looks like before it is an ocean. If the rifting continues and there is no reason to think it will stop, then in tens of millions of years the eastern portion of Africa will separate from the western portion, and the Indian Ocean will flood in to fill the gap. And there will be a new arm of the sea where there are now grasslands and mountains and ancient human history. The Red Sea is the same process, slightly further along. Where East Africa's rift is in its early stages, the Red Sea, the long, narrow body of water between Arabia and Africa, is already a young ocean with a spreading ridge at its center, ocean floor being created, the Arabian plate and the African plate moving apart. It is narrow still and shallow and will not look like the Atlantic for millions of years, but the process is the same. The machinery is the same. The Red Sea is what the Atlantic looked like in its infancy, when South America and Africa were just beginning to separate, when the great tear through Pangaea was new and salt water was finding its way into the widening rift for the first time, and Pangaea itself was not the beginning. This is the last of the things the theory reveals that still carries, even now, a quality of vertigo when you allow yourself to feel it fully. The Earth has done this before, not just once, not just Pangaea, but repeatedly over the full span of geological time, a cycle of assembly and dispersal that has no clear beginning and may have no end. The continents have gathered before and separated and gathered again. Before Pangaea, there was Rodinia, a supercontinent that assembled roughly 1 billion years ago and began to break apart around 750 million years ago. Before Rodinia, there were others, less well-preserved, more difficult to reconstruct from the fragmentary record of rocks that old. The supercontinent cycle, a rough rhythm of perhaps 400 to 600 million years between assemblies, is written into the deep structure of the continental crust in the ancient suture zones where old plates collided and welded together in the preserved cores of ancient mountain ranges ground down to stumps by hundreds of millions of years of erosion in the chemical signatures of rocks that only form in specific tectonic settings. The Appalachians, those gentle, rounded mountains of eastern North America, are the worn-down stumps of a range that was once as high as the Himalayas, formed when the continents that would become North America and Europe collided before Pangaea, before the Atlantic opened. The Caledonides of Scotland and Scandinavia are the other half of the same range, the portion left behind when the Atlantic tore them apart, the same seam split open again. This is what the theory finally gives you when you take it seriously and follow it far enough. Not just an explanation for why the continents look like puzzle pieces, not just a mechanism for earthquakes and volcanoes, but a grammar. A grammar of the whole planet, a set of rules that generates all of it. The mountains and the trenches, the ridges and the rifts, the fossil distributions and the ore deposits, and the climate patterns that depend on the positions of the continents. From a small number of simple principles operating over deep time. It is to geology what evolution is to the study of life, or what atomic theory is to chemistry. The framework that makes the disparate facts cohere. The reason all the separate observations belong to the same story. Wegener saw pieces of the story. He saw the jigsaw fit, the fossils stranded on opposite shores, the mountain belts that matched across oceans. He could not say why it was happening, only that it was. And for that, the physicists of his day were correct to hold him to a standard he could not meet. And he died on the ice, in the dark of the Greenland winter, without knowing that the answer was coming. The ocean floor even then was keeping its record, magnetic minerals cooling and locking in the field direction at the ridge, stripe after stripe of geological history pressing itself into the basalt, waiting for instruments sensitive enough to read it and minds ready to understand what the reading meant. The proof was already there, in the deep water, in the dark. It simply had not been found yet. It would take a war, it would take submarines and the anxiety of navies and the urgent practical problem of detecting things moving underwater. It would take magnetometers towed behind ships in the service of military strategy, and the data those instruments collected would be repurposed, eventually, by oceanographers working in Cold War laboratories, mapping a mountain range longer than anything on land, hidden beneath kilometers of ocean, running down the center of every ocean basin in the world. And from those magnetic surveys would come the stripes, and from the stripes would come Vine and Matthews and Morley, and from that 1963 paper would come the cascade of recognition that settled into the framework of plate tectonics by 1968. The right idea was rejected for the right reason and rescued by the wrong war. The contrarian reading of the story is not that the critics were fools. They were not. Harold Jeffreys was one of the most rigorous geophysicists who ever lived, but that the scientific process was working as it should, demanding mechanism and not accepting beauty of pattern as sufficient proof, and the mechanism arrived from an entirely unexpected direction. The proof came not from geology but from naval technology. The theory was not vindicated by better geology, it was vindicated by better instruments designed for a completely different purpose, operated in a completely different context, by people who were not primarily interested in plate tectonics at all. This is how science sometimes moves, not in a straight line from question to answer, from curious observer to triumphant proof, but sideways through unexpected corridors. A war providing the instruments, a military survey providing the data, a young Cambridge geophysicist recognizing in the pattern of magnetic anomalies the signature of the process that Hess had called geopoetry, and Wegener had called, with no mechanism to support it, the displacement of the continents. The answer was written on the seafloor. We needed to be taught by the particular circumstances of the 20th century how to read it, and now we measure it with satellites. The GPS system, that network of orbiting receivers that tells a phone where it is standing on the surface of the Earth, is precise enough, when operated as a scientific instrument over long periods of time, to detect the motion of the tectonic plates directly. A receiver bolted to a stable bedrock outcrop in, say, Western Europe and another bolted to a stable bedrock outcrop in Eastern North America are drifting slowly apart, year by year, in measurements that accumulate over time into a clear, unambiguous signal. The Atlantic widens at roughly 2 to 2.5 centimeters per year. The Indian plate presses north into Asia. The Pacific Nazca boundary slips at more than 10 centimeters per year. The plates are clocked in real time by instruments in orbit. Wegener could not have imagined the verification. The motion he proposed at a Frankfurt lecture in January 1912 is now measured continuously from space. There is something in that fact worth sitting with quietly in the dark before sleep. An idea born in 1912 from the observation of shapes on a map, the eastern bulge of South America, the corresponding hollow of Africa's Gulf of Guinea, dismissed for decades, mocked at symposia, technically defeated by the best physics available, carried forward by a handful of people who could not quite let go of it, buried with its originator in the Greenland ice, then rescued by a war that had nothing to do with it, decoded by an instrument designed to find submarines, formalized by a generation of ocean scientists working in the 1960s, and finally measured in real time from orbit. One idea, following its long, interrupted, accidental path from observation to proof, arriving eventually at a state of verification so complete and so precise that there is no room left for doubt. And the idea now verified explains everything. Not everything in the sense of answering all questions. The details of mantle convection, the precise forces in any given subduction zone, the timing of future earthquakes, the far future path of the continents as they continue their slow rearrangement, all of these remain active areas of research, incomplete, debated, refined. But everything in the sense of a grammar, the framework within which all these questions are asked, and within which their answers make sense. The distribution of earthquakes, which clusters at plate boundaries, the location of volcanoes which form above subduction zones or along spreading ridges or over hotspots, the height of mountain ranges which grow where plates collide and erode slowly after they separate, the shape of ocean basins, young and narrow where rifting has recently begun, wide and deep where spreading has continued for hundreds of millions of years, the age pattern of the sea floor, youngest at the ridges and oldest at the margins, no ocean floor older than about 180 to 200 million years because all older floor has been subducted, recycled back into the mantle, while the continents preserve rocks more than 4 billion years old because they are too light to be pulled down. All of it fits within the framework. All of it is explained by the geometry of rigid plates moving over a plastic layer, driven by the sinking of cold, dense slabs and the sliding away from warm, elevated ridges within the broader circulation of a planet slowly cooling from within. Somewhere in East Africa tonight the ground is moving. Slowly, imperceptibly, at the rate of a growing hair, the Great Rift Valley is widening and the continent is beginning the long process of tearing itself apart. In 10 million years, or 20, or 30, the eastern edge of Africa will be an island and the Indian Ocean will have begun filling the space between them, and the new sea will be shallow and warm and geologically young. In another 100 million years, perhaps, that sea will be an ocean with its own spreading ridge at the center, its own magnetic stripes spreading outward from the seam where new crust is being born, recording the reversals of the Earth's field in magnetite crystals cooling in the dark. The machine does not stop. The machine has never stopped. It has been running since the Earth was young, carrying the continents across the face of the planet, assembling them and dispersing them, building mountains and opening oceans, writing the whole slow history of the surface in rock and ice and fossil and magnetic stripe. And Everest stands at almost 9 kilometers above sea level, with limestone near its summit containing the fossils of creatures that lived in a warm, shallow sea, and the Himalayas are still rising, and the Atlantic is still widening, and GPS satellites are clocking it all from orbit in centimeters per year, and a German meteorologist who presented a lecture to a Geological Association on the 6th of January 1912 and was largely disbelieved, and who died on the Greenland ice in November 1930 with his idea unproven, who was buried in the ice and never recovered. That man's central intuition turned out to be the grammar of the whole planet. He could see it was true, he just could not say why. And the why, when it came from a direction nobody had anticipated, carried on instruments built for a different war, and it vindicated not just his observation, but the deeper truth underneath it, that the ground is not fixed, that the surface of the Earth is a temporary arrangement, that the continents are passengers on a machine so large and so slow that it is almost impossible to feel moving, but that is moving nonetheless, carrying everything on its surface. The mountains, the oceans, the forests, the cities, the sleeping and the waking. At the speed a fingernail grows, in direction shaped by the sinking of cold rock and the sliding of warm rock and the deep, slow turning of the mantle beneath it all. The passages of the planet are quiet now. The ridge pushes outward in the dark water. The slabs descend into the mantle in silence. The magnetite crystals in the cooling basalt are aligning themselves with the field of this particular geological moment, recording it, pressing it into stone, adding another thin stripe to the barcode that stretches out across the ocean floor on both sides of the seam. Another line in the archive. Another entry in the record the Earth keeps of its own history. If this kind of slow journey has helped you find your way towards sleep tonight, this long walk through the cold and the dark and the deep time of a planet still quietly rearranging itself, there are more stories here of the same slow and careful kind, waiting for whenever you want them. And if you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. It is a quiet pleasure to know the places where people let themselves be still. You have done enough for one night. Put down whatever remains of the day. The plates will keep moving while you sleep. The Atlantic will be 2.5 centimeters wider by this time next year. The Himalayas will have risen a few millimeters more. The Great Rift Valley will have widened imperceptibly in the dark. The Earth is doing what it has always done, and you can rest. Tie off here at the Wisdom Docks. The tide will wait till morning.